Hi, welcome to this lesson on specific heat capacity and specific latent heat. This is the third lesson in topic 14, and specific heat capacity is extremely important in understanding why objects heat up differently to others, whether they heat up more quickly or more slowly, whether they require more energy to increase their temperature or less energy. Specific latent heat, on the other hand, is important in understanding how substances change state. So, let's look at this situation here. On the left-hand side, we can see that it is a hot, sunny day, and the sun is shining directly on this beach. On the beach, we have sand, and we have water. Imagine you're on this beach on this hot summer's day. Would you rather be standing in the water or on the sand? Why? Think to yourself. Obviously, you'd prefer to be in the water rather than the sand, because the sand would be extremely hot. Extremely hot. This is the case even though they've received the same amount of energy from the sun for the same amount of time. But the sand would have heated up far more than the water. They would have received the same amount of energy, but the temperature of the sand would be far higher than the temperature of the water, even though they were initially at the same temperature. This is due to a material property of both the sand and the water, called specific heat capacity. Specific heat capacity of a material is the amount of energy required to raise 1 kilogram of the substance by 1 degree Celsius. This can be used to work out how much energy is needed to raise the temperature of a material by a certain amount. Specific heat capacity can be given by this equation. The word equation is thermal energy is equal to mass of the substance times the specific heat capacity of the substance, this is its material property, times the change in temperature. The symbol equation, on the other hand, is given by E equals m times c times delta theta, where E represents energy, m represents mass, c represents specific heat capacity. The change is represented by the delta symbol, and temperature is represented by theta. The units are as follows. Energy is measured in joules, mass is measured in kilograms, specific heat capacity is measured in joules per kilogram degrees Celsius, and the change in temperature is measured in degrees Celsius. Let's try applying this equation to a question. Pause the video and have a go. Hopefully you've attempted this question now. Let's go through it together. How much energy is needed to increase the temperature of 600 grams of water by 80 degrees Celsius in a kettle? The specific heat capacity of water is 4,200 joules per kilogram Celsius. Now the first step in solving this question is to write the equation. Energy is equal to mass times specific heat capacity times the change in temperature. Now we're going to substitute into this equation. We don't know energy, and that's what we need to calculate, so we'll leave that as E. Our mass is 600 grams. Our specific heat capacity value is 4,200 joules per kilogram degree Celsius. And our change in temperature is 80 degrees Celsius. Now, this is a bit of a trick question, and hopefully you realize that you need to convert 600 grams into kilograms. You can do this by dividing by 1,000. Next, we need to enter these values into our calculator and get our answer for energy. We can now calculate that energy is equal to 201,600 joules. Hopefully you got that. That's it for specific heat capacity. Now let's move on to specific latent heat. This graph shows ice being melted. What's happening at A, B, C, D, and E? Pause the video and have a go. So, at A, we can see that ice absorbs the thermal energy, similar to what we can see in this animation here, and thermal energy is converted into the kinetic energy of the molecules. This causes the particles to move more quickly. We can see that B happens at 0 degrees Celsius. This is the temperature at which ice melts, or it's the same temperature at which water freezes. At this temperature, the ice absorbs a certain amount of energy, and that energy is being transferred to break the intermolecular forces between the H2O molecules. Energy isn't transferred to kinetic energy, but it's just transferred to the intermolecular forces, the bonds between the particles. This causes the particles to move further apart and causes it to change state from ice to solid. This is known as the latent heat of fusion. Next, we have C. At C, the water molecules absorb this energy and it's transferred to the kinetic energy of the particles. Similar to what happened in section A, the particles gained kinetic energy and began to move more quickly. In D, we see a similar horizontal line to B, but this happens at 100 degrees Celsius, the boiling point of water, the temperature at which water boils and steam condenses. At this temperature, water absorbs the thermal energy and it's transferred to break the intermolecular forces or the bonds between the molecules, between the particles. This is known as the latent heat of vaporization. As we can see, as we increase temperature and more heat is absorbed, the kinetic energy of the particles increases from a solid, where there is kinetic energy, but it's fairly minimal, to a liquid, where there's even more kinetic energy, to a gas, where there's even more kinetic energy. This is achieved through parts A, C, and E. We can also see that the particles are spaced relatively close together in a solid. In a liquid, they are spaced further apart. This is achieved through the latent heat of fusion at point B, where the intermolecular forces are broken and weakened. In a gas at the bottom, however, the particles are very far apart. This is achieved through the latent heat of vaporization at point D. Specific latent heat of a material is the amount of energy needed to change 1 kilogram of a material from one state to another without a change in temperature, from solid to liquid and liquid to gas. From solid to liquid, as we know, this is the latent heat of fusion. And from liquid to gas, this is the latent heat of vaporization. Specific latent heat is given in the following equation. This is the word equation. The symbol equation is as follows. And the units. And for the units, energy is measured in joules, mass is measured in kilograms, and specific latent heat is measured in joule per kilogram. Let's apply this equation to a question. Pause the video and have a go. So, in this question, a bath is filled with 60 kilograms of ice. Calculate the energy needed to melt all of the ice in the bath. The specific latent heat of fusion of water is 334,000 joules per kilogram. The first thing we're going to do is write the equation. Next, we're going to substitute from the question into this equation. The energy is still unknown, so we're going to leave that as E. The mass, as we can see from the question, is 60 kilograms. And the specific latent heat of fusion of water is 334,000 joules per kilogram. Now we just need to enter these values into our calculator. This gives us a very large number, and energy is equal to 20,040,000 joules. That's it. I hope you found this lesson on specific heat capacity and specific latent heat useful. If you have any questions, please do ask.